Okay, our new concept today is the stoichiometry of enthalpy. And basically what this is we now have a technique where we can use a balanced equation and stoichiometry to make predictions on how much energy we either need to add or we will get when we do a chemical reaction. And so we need to understand how this works. So the first thing we need to know is that energy can be written as part of the chemical equation, and we treat it as a reactant or a product depending on whether or not the energy is and the reaction is exothermic or endothermic. If it is endothermic, we treat it as a reactant, and it's part of the reactant materials. And if it's exothermic, it's treated as a product. So let's just do a quick example here of what I mean by this. Let's say there's a chemical equation A plus B gives me C. Now, if this is an endothermic reaction, we could write it A plus B plus some heat gives me C. And if it's the exothermic reaction, it's the same basic equation, A plus B, except in this case, it's C plus heat. So if H is positive, we treat it as a reactant. If H is negative, we treat it as a product. And we don't put the minus and plus sign when we do this. The minus and plus sign on the heat only tells us the direction of the heat, whether or not we're losing heat or gaining heat. The heat is still there. It's just whether or not the heat is being gained by the system or lost by the system. It's only a directional of where the heat's going, out of the system or into the system. So when you write your balanced equation, you write your equation and you put heat on either the reactant side or the product side, it's always going to be plus heat. It's never going to be minus heat. I'll show you what I mean by that in a minute. And then when you go to do the actual calculations, you're going to use regular stoichiometry rules and ratios. And then you just treat the heat as part of the original recipe. And then that's it. So let's go through some examples and show you how to do this. Okay, so let's look at a problem here real quick. And I've already given you the answers in the red, but let's see how we walk through it and set it up. So the first thing you have to do is look at our first equation. And here's our first equation right here, right? And it gives me the delta H over here, right? And the delta H is positive. So I'm going to rewrite my equation now to include the heat on the correct side. And since this is positive, I know it's going to be a reactant. So I automatically put it on the reactant side of the equation. And I put it right here, and then I rewrite the rest of the equation as the same. All right. So that's good. So far, so good. And then now we want to do is the second thing is we want to make sure we want to make sure our equation is balanced, right? And I already know that the equation is balanced, but you might do a mental check to make sure it's balanced, right? You want to make sure always before you do any types of these equations is to make sure your chemical equation is balanced, right? So make sure it's balanced. In this case, it is, right? So our first question is asking us how much heat is needed to consume 0.75 moles of sodium bicarbonate. And if you remember back to the naming, sodium bicarbonate is this material right here. Okay, so the same thing as here, that's material. All right, so that's sodium bicarbonate. All right, and it's asking me how much heat is needed to consume 0.75 moles of it. So when we can decompose sodium bicarbonate, we add heat, and we make sodium carbonate and water and CO2. Now notice that for every 2 moles of sodium bicarbonate, we need 129 kilojoules. But I'm only going to be doing 0.75 moles. So the thing to remember here is, or to think about here is, since I'm using less than half, I'm decomposing less than half of 2 moles, I should get an energy that's less than half of 129, right? And that's just a mental thing to keep in mind when you do your check of your answer, right? If you're getting more than 129 kilojoules, then you've done something wrong with your ratios, okay? Okay, so let's erase some of this first. And then the other thing too is remember that I said you have to convert everything to moles, but this one has already been giving us in moles. It's 0.75 moles. So I don't need to do any gram to molar conversion. So I can go right from this to the equation. And here's my equation, right? So my equation is I'm going to start with my 0.75 moles. I know from my molar ratios that 129 kilojoules is for every 2 moles of this. So that's my ratio here, right? So this comes from here, and then this ratio part comes from here. And remember, these have to be the same. All right, so these have to be the same here. You have to say the same for the same units. Okay, so now let's look at this. Now that we've got that all together, now we can just do the simple calculation, right? And the simple calculation says that I can make sure I have my units on the right side, and then I can cancel this, cancel that, and the answer we'll get when we do the math is 48 kilojoules. And that makes sense because this is less than half of 2, and therefore my answer is less than half of this. Okay? Now let's look at another problem real quick, just to show you it's a little different and requires one more step, right? So in this case, it's asking me how much heat is needed to produce 200 grams of sodium carbonate, right? Sodium carbonate. And that sodium carbonate, you remember back from your naming thing, is this material here. So that's sodium carbonate, and I want 200 grams of it. Okay, so remember grams is not moles, so we're going to have to do our first thing is convert to moles. So let's do that first. Let's convert to moles, and we've done it here. There's 106 grams per mole of sodium carbonate, and I'm starting with 200 grams of it. So I have almost 2 moles of material, almost, not quite, almost 2 moles of material, right? And I do know for every 1 mole of this, I need 129 kilojoules because that's my ratio, 1 to 1 of these, right? So now I have 2 moles of this almost. I'm going to have about 2 moles, 2 times this number here for energy. That's just a mental check to make sure that when I get my answer, I'm doing it right? And so when we do the math, and we're doing the math again here, we have 1 mole of this. This is for my ratio above, right? Remember, 129 joules for every 1 mole of this, right? So there's my ratio from these two, right? And then here's my molar mass ratio to convert from grams to moles. So this will cancel here. And then when you do all that, you get the answer that you need right here, which is 243, right? And that makes sense again because look, 129 kilojoules for every 1 mole of this. I have almost 2 moles, so I should have almost about 260 if I had 2 moles, and I have 243, and that makes sense. So that's a good mental check. All right, so you see how we set this up. You should be able to do this now on your own. We'll do one more practice problem on the next page and show you how to do it. Okay, so I want you to try this problem on your own, and then when you're ready, we will walk it through together. So the problem here you're going to do is, I've already set it up for you. So this is the problem you're going to use to solve. This is the equation you're going to use to solve these 2 problems, this one and this one. And what I'd like you to do is to, when you're ready, is to stop the video, copy down the information that you see here for this one and this one, work through the problem, and then restart the video when you're ready, and I will walk through it and how I solved it, and we'll go from there. Okay? So you can, when you're ready, stop the video. Okay, so let's set this up now and show you how we do it. So first thing we want to do is erase some of the stuff here that we've done to give us more working room. Okay, so the first thing I'm going to do is when I look at this, I'm going to say it's asking for how many moles of CaO must be reacted to produce 20 kilojoules of heat. And I looked at my equation here, and if I need 20 kilojoules of heat and I get 65.2 kilojoules from this part right here for every 1 mole of this, then I know when I do solve my problem, I should be using about a third of a mole, basically roughly a third of a mole, because 65.2 kilojoules for every 1 mole, I only need 20 kilojoules, and 20 is about a third, a little bit less than a third, about 30% of 65. So if my answer is significantly different than that, then I've done a calculation wrong. But let's set it up to make sure we've done it right. Okay, so the first thing I want to do is, what I'm given is my 20 kilojoules, so I'm going to put that here. And then I'm going to multiply it by something. And I know that for every 1 mole of this, I get 65 kilojoules here, so I'm going to put 1 mole of CaO. And then on here, I'm going to put 65.2 kilojoules, right? And that's it, because that's going to give me the number of moles. When I do my thing here, I'm going to get the number of moles, and the answer becomes 0.307 moles of CaO. All right, so there you go. That's how I set it up. It's pretty straightforward, pretty simple. If you set it up the same way, give yourselves a pat on the back, then you seem to have mastered how this works. Let's just do the next one together, all right? So now it says if 0.25 moles of water are reacted, how much heat is produced, right? And I know from my balanced equation up here again that 1 mole of water here gives me 6.52 kilojoules, right? And if I have a quarter of a mole of water, I should get about a quarter mole of this. So let's set it up to make sure that we do that. All right, so here we go, 0.25 moles of water, H2O. And then I have to make that a molar ratio of something, right? And I do know from whatever my thing here is that 1 mole of H2O, according to this, gives me 65.2 kilojoules, right? And that equals 16 kilojoules, roughly, you know, almost 16 kilojoules. With significant figures, it's 16 kilojoules. All right, so you should have gotten that too, and if you didn't, see how I did it, and you can work through it, and there you go. Okay, so this is just the answer set that were on the slides. Again, just a double check to what I've done. But remember this is the critical part of this whole thing, is that you have to get the right molar ratio of your what you're looking for versus what the energy is. So I was looking for moles of this, and I know that 1 mole of that gives me this is how much energy I have, and so that's the ratio I use here. And the same thing, you would go down here, for every mole of water, I get this much heat. And so there's my mole ratio there. So it's fairly straightforward. If you've got it, then you should be able to do well. Okay, so let's do one second to last trial practice problem for the video, and then you'll be on your own. You can do the worksheet. So here's a problem that we want to try, and again, the same thing is try it on your own, then come back and see if your answer matches one of the ones here, and I'll work through it with you. So stop the video anytime, and then come back when you're ready. Okay, so I've done the equation for you. I've set up my work thing, and I showed you where I will quickly walk through how I did it. So here's my starting material. I'm asking for 28, this thing here, so that's from here. So that goes to here. And then I know my molar ratio, I calculated that, of sodium oxide. and that's 62 grams. So I converted everything to moles using this ratio. And then I know that 1 mole of sodium oxide from my balanced equation gives me 120 kilocalories. So that's my molar ratio here. And then when I do the math, I get 48 kilocalories, which is the answer C. So if you've done that well, then again, you seem to have mastered this well. Okay, so here's our last practice problem for the video, and then you're going to be required to do some practice on your own on some worksheets, or if this was just a review, I hope this was helpful. So our last reaction is 2 moles of chlorine gas plus 7 moles of oxygen gas. We need to add 543.4 kilojoules to give us 2 moles of dichlorohept oxide. Right, dichlorohept oxide, that's this material here. And I'm asking to calculate the energy required to produce 7 moles. All right. So again, you want to go when you set this up on your own, and then come back when you're ready, and we'll solve it together. Okay. So turn off the video anytime you're ready. Okay, so you're back, and I've already set this up and showed you how I did it. So I had 7 moles was my starting amount in my halve, and I put that here. And then I multiplied it by the correct ratio. I don't have to convert it to grams or any. I don't have to do any conversions because it's in moles, and we always do stuff in moles when we do the ratios. All right, and then, then what we do is we see how many moles of dichlorohept oxide for every 543 kilojoules of material. We can see that there are 2 moles of that for every 543 kilojoules. So that's my molar ratio here, or my ratio. And when we do that and we multiply everything out, we get 1900, almost 1900, about 1900 kilojoules per mole. Kilojoules, not kilojoules per mole, just kilojoules, right? Because we've taken care of it with the mole thing. And so our answer is D. So you should have a good understanding of how we do this now. You've seen several iterations where we've put the we put energy on the reactant side, we put energy on the product side. We've had to convert to moles. We've had to convert out of moles. So you should have a good way of doing it. And practice your stoichiometry, practice this, and you should be pretty well, understand this pretty well. Okay, so I just wanted to have a last slide, wrap-up slide of the takeaways from the learnings that we've tried to, on the concept we've tried to do here. So the amount of heat can be gained, the amount of heat gained or lost when we do a chemical reaction can be calculated using a balanced equation and the heat of formation for that reaction. And then if we treat the heat of formation like a reactant or product, reactant if it's gained heat, or product if it's lost heat, as shown here in these types of equations, right? Then we can use normal stoichiometry ratio rules to determine the amount of heat. And we had several practice trials to do that, and you should understand now that you just treat heat as it would be any other type of reactant or product, right, when we do the ratio, right? And so if you have 2 moles of A require 130 moles, 130 kilojoules, then the ratio would be 130 kilojoules for every 2 moles of something, 2 moles of A. And that will change depending on, what material you're looking at here. But if you use the normal stoichiometry ratio rules and a correct balanced equation, you should have no issues on doing this, as you would a normal stoichiometry problem that does not involve heat.